Welcome to another video clarifying various aspects of relativity and quantum cats. This one is intended to provide an easy-to-understand visualization of kinetic energy and of the famous E equals mc squared equation, the Einstein equation. As usual, I'll be using a non-standard space-time diagram to represent the relationship between bodies in relative motion. It's based on an equation fundamental to relativity called the Lorentz transformation, a solid basis which can't be credited to the commonly used Minkowski diagram, which I've critiqued in several videos linked below. Bear with me on a little introduction for just a minute. The horizontal axis here represents the 3 dimensions of space, and the vertical axis represents the dimension of time. As an observer A moves 10 seconds in time, a body B moves a relative 8 light seconds in space, and its clock appears to the observer to tick only 6 seconds. Anyone familiar with space-time diagrams will note that there are no so-called light cones here. Light cones are an artifact of unrelativistically projecting the clock speed of an observer onto the clock speed of a body in relative motion. That is, or should be, a relativity no-no. What is striking and instructive about a truly relativistic diagram is that the vector of a light ray moves along the space axis of an observer, not on a diagonal a la Minkowski, simply because if a light ray had a clock, it would not move in time. See if you can figure out why each vector, each world line in this diagram, is necessarily of exactly the same length. Several remarkable features of the nature of light can be derived from all this, but not now. Enough preparation. Now for kinetic energy. I've added here a sort of 5th dimension to body A to represent its quantity of mass. Mass is not actually a dimension, of course, but displaying it as such can be helpful in understanding kinetic energy. Body A has a velocity v of 0 and a mass m of 4 kilograms. The standard formula for kinetic energy shown here is not relativistic and not precise, but the relativistic version is highly complex, and it is not needed to provide a basic understanding of kinetic energy and of Einstein's famous E equals mc squared. The equation says the kinetic energy of a body is equal to its mass times its velocity squared, with both the mass and the velocity also being halved. V is squared in the equation because kinetic energy involves the acceleration of one body by another. V unsquared would involve just uniform, constant, singular motion. The equation was first conceived in the 18th century without the 1/2 divisor, which was only added early in the 19th century. The difference needs to be explained. Body B is the one in relative motion, so it is the one with kinetic energy, leaving relativity aside. B is described as having a mass of 4 kilograms and is moving at a relative velocity of 2 kilometers per second. Solving the equation, 4 times 2 squared equals 16, divided by 2 equals 8 joules. Joules being the name for a quantity of kinetic energy. Not a lot of joules, but it's just an example. Now if B impacts A, the result will be as predicted by the equation. Put simply, the divisor 2 expresses the resisting force that is needed to counter the kinetic energy. If we just consider B before it clashes with A, it has kinetic energy, but as yet no resistance. So at that point, the divisor of 2 is not a relevant factor. If B is not yet interacting with A, let's strike out the more modern version of kinetic energy and consider the energy exclusive of its effects. That's the crucial difference between the 2 versions of the kinetic energy formula. In this one, we are looking at the exclusive kinetic energy of a single body. In the other one, we were evaluating its potential or subsequent interaction with another body. I think this version makes it pretty clear where Einstein was going with his famous hypothesis. He was interested in the energy of the body itself, not the result of any subsequent interaction. Given the theoretical equivalence of mass and energy, the question he posed was, what if mass could be somehow converted to pure energy? Could it even be possible? The annihilation of 4 kilograms of body B would yield 4 times the quantity 300,000 squared, or 360 billion joules of energy. Confirmation would come in 1945 with the detonation of a nuclear bomb. E equals mc squared is widely considered one of Einstein's greatest insights. But given his relativity theories, the special and the general, truly his greatest insights, given his recognition that the speed of light is an absolute limit denied to mass and restricted to light, and absent the obsessive, obtuse mathematical formalisms of postmodern physicists, E equals mc squared is almost obvious. I hope you found it relatively easy to follow along here. If you still want or need to learn the mathematics, I believe a good grasp of the concepts makes the details a lot easier to master. As I'm sure you know, it's almost impossible to get a YouTube video notice now that there are so many established oldies with hundreds of thousands of hits already and capturing the searches. So please give this a like and a comment or question, and tell your friends and neighbors.